Hello everyone. Welcome to the Climate Change and Coming Challenges of Land and Fire Management webinar. This is David Christensen. I'm the Acting Center Manager of the Wildland Fire Lessons Learned Center in the United States. We've got people on this webinar from around the world. We'll get a count in just a little while and give you more information on that, but I wanted to welcome everyone to this very special learning opportunity. Turn it over to Chuck Bushy now from the Interagency, or the International Association of Wildland Fire that we're working with on this co-hosted webinar. Chuck?
Thank you, Dave. Again, I would like to welcome everybody to this second in our international series of wildland fire topical webinars. I think this one's going to be especially interesting to a wide audience. We know that there's been lots of talk of climate change and potential impacts at various upper government levels, but there seems to be a lot of confusion down on the ground how some of these impacts may be affecting individual people, individual tracts of land within our various land management organizations. So hopefully we can learn a little bit from the experts that we have on today. The moderator for today's session is David Ganz. David is a senior scientist with the Nature Conservancy's Climate Change team. He's also a visiting scholar with the UC Berkeley Center for Fire Research and Outreach. David is an expert in fire science, policy, and management, who also has experience integrating forest and fire science with some of conservation's more important new opportunities and emerging issues, such as sustainable livelihoods, climate change adaptation, ecosystem services, avoided deforestation and degradation, and community forestry. Dave's also worked for the UN's Food and Agriculture Organization, positioned at the Regional Community Forest Center in Bangkok, Thailand. In his role with FAO, David managed a variety of projects focused on southwestern China and Southeast Asia. Most recently, he was a senior scientist in charge of forestry and fire science projects for TSS Consultants and vice president of international operations for Renewable Energy Institute. I'd also like to add that David is a new board member for the International Association of Wildland Fire. So I'll turn it over to David, who will be our moderator, and let him take over this session. Thank you, everybody, for attending.
Thank you very much, Chuck. I'm going to be moderating the panel today, and it's really a distinguished privilege to moderate this panel. We have four speakers today, starting with Mary Lata, then Bill Sommers, Mark Kaib, and then Tom Swetnam. And we're actually going to be taking questions towards the end of this webinar, and occasionally we'll be polling you to find out exactly where you guys are coming from, what some of your issues are. And I'm actually going to initiate a poll right now so you can see how it works. But as you will see with your display here, you will have a poll pop up on your right-hand side. The first one is going to be, what is the best description of your career, your actual professional track? And so we want to get a sense for who you are, where you're coming from, what some of the issues you're having in climate change adaptation and climate change mitigation. So with that in mind, for asking and answering questions, we would prefer to do that towards the end. At the bottom of your chat window, there's two windows, one that says questions and the other one that says chat. Please use the one that says questions. We will be taking them one by one, and if you could address your questions to specific members of the panel, that would be very useful for me as the moderator. First and foremost, I'd like to introduce our first speaker. Mary Lata is a fire ecologist at Buffalo Gap, Fort Pierre, and the Oglala National Grasslands. This includes McKelvey and Nebraska National Forest. And Mary's first exposure to fire was in the 60s as a kid, watching retardant drops in Glacier National Park. She thought that was pretty neat, so she decided to take on a career in fire. She earned her PhD at the University of Iowa in geosciences, studying the relationship of soil moisture and thermal dynamics of fire in both mixed and tall grass prairies. And over the last 18 years or so, she's worked for the Nature Conservancy, the Park Service, and the U.S. Forest Service. And she's worked in fire effects, fire suppression, fire and fuels program management on the planning and administration side, as well as research. So without further ado, I'd like to introduce Mary and have her take over as our first panel speaker.
My presentation is largely to put out those questions and concerns that I've experienced or I see other managers on the ground experiencing as we go about our business of land management. The concerns that come up about what do we do with the upcoming questions for fire and climate change as it relates to our administrative jobs and implementation in the field in particular. So to initially boil it down to one question, I put it at what information is needed for effective land management in the face of climate change and fire. Our job is to manage and make observations and monitor what we do. And on a larger scale, climate change data as it comes down from whether it's a global climate model or other forms of extended research has to be usable at the various scales. Policy direction from whatever level it is, globally down to agency-wide in whatever country, planning scales. Patch size is important, and the continuity of the landscape as well. If we have fragmentation and we are talking about the same fuel type or the same ecosystem, in one case it's fragmented, in another case it's not, how is that going to change what we can and can't do once we even realize what that is with climate change? And implementation, of course. When we get to landscapes that may be on a threshold, do we still want to burn it? Do we know what's going to come back later? Those are some of the concerns we have. So to take it to a more specific example of sorts, let's say that several GCMs agree that on a given piece of land we are likely to see an increase of about 3 degrees over the next 30 years. That information by itself is not useful for making land management decisions, for writing a forest plan, and for deciding what to do. It's a very important piece of information, but from a manager point of view, if we're talking a forest district or a park, we need a lot more information, and that leads to a lot further questions, a lot more questions, such as there's going to be a domino effect. We know that if the temperature's changing, there's going to be a lot of other things that change, and we need to have some idea what to expect so we know what we need to be doing on the land. For researchers, looking at and identifying not just the change in temperature but the other things, and then translating or helping us translate those into consequences for a local ecosystem is important. That's where, for the manager on the ground, we start to try and figure out exactly what we need to do, long-term and short-term. When we're out there on the ground, we need to know what to be looking at. How do we identify a changed landscape or changed potential on a landscape? What do we need to be monitoring? When we're looking at our range and wildlife programs, at our fuels and fire effects programs, we have protocols already that will tell us what the general process is that we need to follow when we're documenting what the effects of our management is. So when we're throwing climate change into the mix, that makes it a lot more complicated. When we see a change, is that good or bad? We have in the Forest Service anyway, we use what we call management indicator species, and that is our canary in the coal mine for whether or not we're doing the right thing. That will show us that we're moving the right direction or not. Those management indicator species are likely to change as the potential of the landscapes change, and the potential will change on a number of scales. once it does change, or as it changes. A big question we've had is how are we going to identify what should be there? Or once we have a changed landscape, as the soil would start to change slowly too, what is it that's going to be out there and sustainable and healthy on the landscape? We may see new species coming in, new species dominating, new combinations of species. And learning to identify which ones of those are going to be sustainable under the changed conditions is a real question for us right now. All the disturbances that we deal with on a regular basis, whether it's fire we're all familiar with, and that's why most of us are on here, but there's interactions between all the disturbances as well. And as part of just being human on this planet, we've changed some of the disturbance cycles, as well as the interaction of some of the disturbances within themselves. Fire, I think, I'm particularly interested in noticing when I started putting this together that in listing all of these fairly standard disturbances, the most common ones, fire is one that we seem to have a real bipolar relationship with. On one hand, we spend lots and lots of money and time and effort trying to suppress it, and on the other hand, we do the same trying to put it back on the landscape and trying to understand what it does. For the others, with the possible exception of grazing, we rarely actually put it on the land. We try and mitigate it if we can. But there are interactions between all of these. In some cases, this is a typical grassland. Drought in general, when we talk about it, people think about forested landscapes becoming more and more flammable as time goes on. Certainly trees die out, they become stressed, and particularly in areas where there's a fair amount of duff, they will be quite a bit more flammable for a while. In other areas where, in particular, you have herbaceous fuels at the surface, what you're looking at now is the third or fourth year of drought, and 2004 was actually a fairly wet year. It's up here in the northern plains in the United States. The next few years were very dry, and as you'll see, this first year coming up responded to the moisture in '04 by producing a fair amount of biomass, but then it all dried out, and in the next few years you can see what happens to the potential for fire on that landscape. So in the forested areas where there's a lot of woody growth and woody vegetation, you probably would see an increase in flammability over the series of years in a drought. This is in the northern plains, and to a different degree this is going to apply to different grassland areas. In an extended drought, you'll see a decrease in flammability after the first few years, depending on the productivity of your system. In some data we had from the sandhills, going back to about 1905, we saw a significant decrease in fire occurrence during the Dust Bowl in the 30s, probably because there wasn't as much fuel on the ground. So that's an interaction between drought and fire, and that's one that we've messed with a whole lot as we get really good at fire suppression and don't put it back on the ground. When we bring it back to climate change and just the interaction of different disturbance cycles, how do we identify what's happening and assign a cause so that we can start to understand what's going on with the system? This first bullet here, we're not too bad at that, understanding what changes have been wrought by current and historic fire management. But when we start throwing in current and historic management of other disturbance regimes, the drought, the drought, the grazing, insects, and so on, and then we relate it to climate change, and you throw those all together, it gets a lot more difficult. And fundamental to many of our systems are these interactions. So we change the potential for these systems, the potential natural vegetation, and I want to look just briefly at soils here. Everybody knows soils are, without soils we don't have fuels, we don't have fire. And the way they're distributed across the world, I'm going to talk about molluscs a little bit. That's represented by green here across the landscapes, the pampas in southern South America. In particular then, if we look at molluscs, they sequester, as soils go, a fair amount of carbon. And the research I've read and looked at, particularly in the more productive grasslands, the tallgrass prairies and the wetter portions of the mixed grass prairies, they're going to sequester a lot more carbon when they burn on a fairly regular basis. Grazing tends to do the opposite. So when we're decreasing the fire as it occurs on those landscapes, what is the long-term effect on the soil? Across the world, there's a fair amount of mollisol. There are a fair amount of mollisols out there, and I don't have a number for what percentage of those are represented by the most productive grasslands, where you have more carbon sequestered in the richer soils there. And they also, coincidentally, or not so coincidentally, are represented by the more frequent fire regimes. On the bottom right there, in the dark and light green, are the fire regimes 1 and 2, where fire return intervals are less than 35 years on average. And in the top left, the dark brown shows where 75% of the soils or more are mollisols. And not surprisingly, there's a pretty good correlation there. So when we start decreasing fire in these systems, my question is then, what is the effect on the soil? What is the effect on the long-term potential of that landscape to sequester carbon, to support some sort of a natural disturbance regime? Are we going to allow these natural disturbance regimes, and where? So here was something that I put together to sort of get a handle on the changes that we are making on the landscape. What we're looking at here, take ponderosa pine as an example. This is a fuel model 2 using Anderson's fuel models. And in this particular case, taking the fire return interval is 7. That's taken from the FEIS, Fire Effects Information System. And I don't have it labeled here, but this represents BTUs. So for 1 square foot of a fuel model 2, the first time it burns, that's the green down here, it produces this many BTUs. The return interval is 7, so after year 5, it won't have burned again, so that hasn't changed. These are cumulative. So we go on to year 20, and after year 20, remember we're on a 7-year fire return interval. It would have burned in year 1, would have burned in year 7, hasn't quite burned again. So we've got cumulative here, and if we take this out to 200 years, this is what it looks like. This represents under average conditions on 1 square foot of land, and these different fuel models, sorry, that's my phone ringing there, how many BTUs would have been produced if it was on an historic, fairly healthy return interval. And talking with folks I know in land management and areas that I work with, this is what it looks like based on our current fire return interval. So again, if I'm thinking about what are the changes that we are putting on the land based on our management of fire suppression, prescribed fire, and then try and extrapolate that a little bit to what's likely to happen with climate change on a much grander scale, I'm a little concerned about what we're doing on a much more permanent basis with the soils in particular, the potential. So if you throw the changes to the soil in and extrapolate that to the fuel models and how and if and when it can burn, and then throw in all the different fuel models and the different agency policies and protocols, it turns into a pretty complicated question. And trying to then whittle this down to a single question, again, although I've raised a number of questions, I put it at how do we identify our priorities and set trigger points for management decisions in the face of climate change. That's what I have.
Thank you, Mary. I just got a few folks on the questions that realized that there's a little bit of a lag time between when the poll finishes and when the PowerPoint starts up again. So if you happen to have such a lag time, just hold on, and it will indeed come back. So I'd like to share the results of our first poll, which was what is the best description of your current position. We have on the phone today about 25% of us are researchers, 37% are fire managers, 9% are land managers, 5% are administrators, and the other 25% are other. And I'd like to start one quick additional poll now that Mary's presented. Do you or the unit you work with currently do any monitoring to identify the potential effects of climate change? And so I'm about to launch this poll. Please take a few minutes to fill this out, and then we'll move on to our next speaker. While this poll is being filled out, I will begin the introduction to our next speaker. That's Dr. William T. Sommers. Dr. Sommers is currently a research professor in the College of Science at George Mason University, where he serves as chief scientist at the Mason Center for Climate and Society and the co-director of the East Fire Laboratory. Bill is a former member of the board of directors of the International Association of Wildland Fire, one of our co-sponsors today. And prior to joining George Mason University, Dr. Sommers spent 30 years in the research division of the U.S. Forest Service, serving as a director of the National Research Programs. In that capacity, his research area responsibilities included forest fires, global change, carbon cycle, invasive species, quantitative ecology, ecological risk management, and sustainable forest management. He was a member of the NWCG, International Boreal Forest Research Organization, and the Roundtable on Sustainable Forests, and he was an active member in the White House Science Committees on Global Climate Change and Ecological Systems. Dr. Sommers' academic training is in the fields of atmospheric science and geophysical fluid dynamics, with degrees from the City College of New York, Massachusetts Institute of Technology, and the SUNY University in New York. And he's had additional training at the MIT Sloan School of Management. So without further ado, I'd like to turn things over to Bill Sommers.
Thank you, Dave. Let me just bring up the PowerPoint. So how do we go about getting or gaining an improved understanding of the connections between fire and climate in order to prepare for climate change? We need to acknowledge some basic conditions. Climate in the 21st century will differ significantly from climate in the 20th century, and climate change will significantly alter ecosystems and fire regimes. 20-plus years of climate science is now being called on to inform climate action, and the climate action items would be things like planning, mitigation, adaptation, coping, triage, and risk assessment. And fire management will play a critical role in each of these. What are some of the pieces needed to improve our understanding and better inform fire management considerations for climate change actions? Looking at Earth system components, you have to understand the background in terms of the atmosphere and its chemistry, the atmospheric dynamics, and ecosystems with particular importance of fire. We also have to be mindful of what I call the information pedagogy, of the source and reliability of information that we provide our user community. We have to understand what we're talking about as something that we observe or know, something that we interpret or understand, or something that we forecast or expect. In terms of fire, we know or observe that would be fire history. Things like just the observations of fire, written history, paleo fire, and so on. In terms of how we interpret and understand that information, we'd be talking about fire regimes. And the particular importance or view of this webinar is how climate change will affect fire regimes based on our knowledge of fire history. In addition, we need to be cognizant of all of the work that's gone on in the global change arena in terms of information and assessments. which drive much of the policy considerations and much of the information that is driving the agencies. What are some of the pieces needed to better inform fire management and planning for climate change actions? Throughout this, you have to be very cognizant of scales of time and space in terms of the information, in terms of the environmental change, and in terms of the actions that are taking place. In the atmosphere, scales, the ecosystem scales, and scales of fire management. Scales in the atmosphere include climate change and variability, the seasonal to interannual planetary wave or El Nino scale, and day-to-day weather. In terms of ecosystems, I think a very important meeting ground is the Bailey system of domains, divisions, provinces, and sections. And finally, we need to be cognizant of the scales involved in fire management. Fuel conversion over time and distances, seasonal planning, and at the event or incident scale. So how should we use fire history and climate science knowledge to better inform place-based climate actions that Mary was talking about? What I'm suggesting is that by feeding the fire history type of knowledge and climate science knowledge through an understanding based on climate classification, ecosystem classifications, and fire regimes is the best place to start to produce that place-based climate change action information that the managers need. Just a reminder for those who don't have it current in their minds, this is what a Kirpin climate classification looks like for the United States. And the basis of the Bailey ecosystem regions, in which at the domain level and the division level, climate is the determining driver. As you get down to the province or section level, other factors come into play, and climate is not the sole determinant, but an important driver. Again, the Bailey ecosystem domains level, the divisions level, and the provinces level. I'll wait for the audience view to catch up. Now, in terms of fire regimes, the level of resolution, and this is fire regime condition class, is basically gets down to the province and smaller scale. We need to synthesize information about, therefore, the atmosphere, ecosystems, and fire management over multiple scales, and produce a synthesis, and by that I mean the composition or combination of parts or elements to form a whole, the combining often of diverse conceptions into a coherent whole. So basically to take this information at multiple scales and synthesize it for management use. Now, we also have to be very mindful of what I call the information pedagogy, the information that we're presenting in terms of, do we know it or have we observed it? Is it something that we interpret or understand, or is it something that we forecast or expect? In terms of what we observe and what we know, there are observations, meteorological, written histories, and so on. There is our knowledge of Earth history, and there is our knowledge of climate history. These are things that we know and observe and can bring information towards the managers to use. In terms of how we take that information and interpret or understand it, Newtonian physics and thermodynamics are the basis for most of the atmospheric modeling, general circulation models, Bayesian logic, and ecosystem understandings, how we interpret that in terms of ecosystem units. In terms of what we forecast or expect, we can figure out that tomorrow is going to be like yesterday, nothing's going to change. We can use our knowledge of fire regimes and other empirical types of information and extend that into a less certain future, or we can use computational models of the future, such as the general circulation models. And I would posit that most of the arena that we'll be working in for the next decade or so is working in this empirical extension arena, in which we're using fire history and fire regime information to forward our information. Now let me quickly go through what I consider the system components that are important, central to the issue. In the atmosphere, we have atmospheric chemistry, atmospheric dynamics, and ecosystems. And looking at the climate change game and information, I always like to start with the work of Charlie Keeling, who began taking observations at Mauna Loa Observatory in Hawaii of carbon dioxide in the atmosphere. And when he first got his measurements going, his first complete year was 1959, he measured 316 parts per million at Mauna Loa. Why was he interested in this? Well, in 1896, the Swedish chemist Arrhenius figured out how the Earth's atmosphere stays warm, is impacted by greenhouse gases, and how the atmosphere works chemically. Keeling felt that based on the use of fossil fuels, that the carbon dioxide, one of the primary greenhouse gases, should be increasing and should be measured. In the 50 years since Keeling began his measurements, the CO2 concentration has increased to 391 parts per million, which, as you can see, is a significant increase in the amount of time of a half a century. The other piece, and you hear a lot about general circulation models, is understanding atmospheric dynamics. This field really began in the early part of the 1900s with the Norwegian School of Meteorology, was advanced in terms of numerical weather prediction by Lewis Richardson in 1922. At this time, the equations for predicting future weather and climate were in place, but the digital computer systems needed to do them were not available. This did not take place until the early 1950s. And the same models that were used by Richardson, Charney developed what are the current models for predicting day-to-day weather, and Phillips began developing from the same basis the models that are used to predict global circulation models for climate change. And this is the basis when you see these charts in the various assessments of what's going on. In terms of ecosystems, I already mentioned Kirpin. In terms of the climate ecosystem relationships, Holdridge life zones, and daily ecoregions, which we in the number of the agencies depend on very heavily. And this leads to projections of, in fact, how climate and net productivity, and one of the things Mary touched on, is this, on a global basis, shows the relationship that if you grow more, you have more to burn. Very quickly, because you need to be aware of it, but won't go into detail, there is a vast history of various assessments at the international level that play into the information that needs to be synthesized for managers. And these are the assessment reports, but I want to in particular focus a little bit later in this talk on the general circulation models and on the emission scenarios. We also have a lot of reports coming out of U.S. government agencies that are available for informing our knowledge and decision processes. Okay, well, I'm not sure how much we missed, but I'll be going through on the continuation of some basic information we have showing the increase of global temperatures and increases of carbon dioxide concentrations with temperature changes, basics of the climate change science. 100 years of changes in carbon emissions, CO2 concentrations of temperatures showing, in fact, lockstep between carbon emissions, CO2 concentrations, and temperature. And comparing 140 years and the last 1,000 years in terms of, for the northern hemisphere, changes of temperatures on a global basis. The level of knowledge and modeling has increased tremendously. And in fact, if you look at a comparison of models with just natural forcing and models with just anthropogenic forcing, which compared with models and observations for the actual change in climate, you see a very close correlation between the modeling that includes both anthropogenic and natural forcing with the actual climate record in terms of temperatures. Now, I want to touch briefly on areas of uncertainty in terms of the atmospheric components, and I think this is important to understand and to bring into considerations. A lot of the uncertainty that exists is not actually in the atmospheric dynamic sides, the general circulation models, but it's in the underlying scenarios that go into the basis of formulating the future direction of general circulation models and climate change. And basically, the dynamics of the atmosphere need input in terms of the chemistry of the atmosphere. And the only way that we can get a future projection of the emissions and concentrations is to build a series of scenarios based on energy use, population change, and so on. And these were done in 2000 as an IPC special report. And as you see the climate literature, you'll see mention of an A1, B1, B2. These are all the big basic scenarios of emission changes based on assumptions of social, economic growth, fuel use, and so on. Now, as you look at the changes over time that are projected, and on the left here, these are projected with low, moderate, and growth, high growth scenarios of the emissions projections for the 20 to 29 and 90 to 99 period of time. The point I'm making or want to bring out is that there's more uncertainty associated with the projections of the future population and energy growth and international policy in terms of greenhouse gas emissions than there is in the actual general circulation models. Very recently, in fact this month in Nature, the effect of the Copenhagen Accord was looked at, and again what it shows is that uncertainties in the projections of human use of power and of emissions controls add a lot more uncertainty to what we understand than to our general circulation models. And I just put in, what was talked about now, is a 3-degree line of global warming by the end of this century. In terms of the GCMs themselves, they have moved tremendously in terms of convergence. Again, they agree for the emission scenarios very closely. Through a period of time, they've increased their complexity and things that they bring in to the equations, and they've increased, and these are the first, second, third, and fourth assessment reports of the IPCC, in which the resolution is increasing. I think over the next decade, what we're going to see is a tremendous increase in resolution, both in time and space, and start moving into predictions of the interannual to seasonal variability. Just again, the model evolution, so you're aware of it, moved from the early 60s in which only the ocean and the atmosphere were included in the models to the present time where all of these factors are included in the circulation models. Now, what does it all mean in terms of what's available? Well, again, there's a tremendous amount of literature out there that needs to be interpreted for on-the-ground use. But for various different scenarios, there are significant changes both the winter and summertime, temperature, precipitation, sea level pressure that can be expected. Changes in precipitation, soil moisture, runoff, and evaporation are all involved and predicted. And global average changes in precipitation for the various scenarios are available. Changes in frost days, heat waves, growing season. But what does it mean in terms of ecosystems and fire? Well, again, it goes back to scaling, but we have a rich history in the United States of fire history that I think can be brought to bear on the subject. And we have reconstructions, again, in that fire history data and climatological data of ice core information, reconstruction of biomass burn, reconstruction of fire frequency, trends in woody biomass, biomass burning, and dates in fire. So all of this information exists and is available for interpretation. We also have a history in terms of the fire information that we need of how fire moves through time from millions of years ago to the present, and this has all been laid out and is available for downscaling and providing information. Now, in terms of a global basis, this is a projection from satellite information of active fire detection and of area burned. And in terms of current pyrogeography of the Earth, areas of not primary productivity and the average number of fires observed by satellite. And what you find is, of course, where there is fuel to burn, there is fire. And this is, again, well known to the fire community, but information that we need to bring forward as we move into climate change action through the interpretation of climate change as it affects through Bailey's ecoregions. Now, as an example of that, this is some work that was recently done that ties wildfire regimes in the United States to the Bailey ecoregions of the country, large versus small wildfire areas, recurrence intervals, and so forth. Again, at the Bailey's level, bringing it down to a finer scale, work is done and is available for various parts of the country that translate the climate change information from the larger general circulation models to the Bailey type of divisions. And as we look at fire activity in terms of, again, satellite tracking, using different models and different approaches, we can map for both inclusion of net primary productivity into the fire models and without net primary productivity, how the world looks today, and then projecting that into the future, both in terms of with and without net primary productivity, how different areas of the globe are likely to change in this century in terms of fire activity. And of course, the take-home message is that for either including or not including net primary productivity, we're looking as we move through the century for increased fire activity resulting from climate change in the United States. Now, I want to quickly go through, if I have a few minutes, sort of relationship that brings us back down to some real things in fire. Again, you can never make a one-to-one correlation between climate change and what happens in a place, but the fires in Australia of a year ago have a lot of the hallmarks of things that we as fire managers would expect to see under climate change. We went through a period of drought prior to the fires that's seasonal to interannual variability. We had an exceptional heat wave. We had meteorological conditions Okay, I'll just wrap it up there. I've lost screen sharing again. Why don't I turn it over, Dave?